I've always wondered if the Saturn V was able to reach Mars. If you think about it, it should be possible, since we have sent rockets that are way smaller all the way to the Red Planet. We first have to see the math behind the Apollo missions for comparison. To start it off, the Apollo missions were basically a math equation waiting to be solved. The engineers and mathematicians had to first calculate how they would get off the ground into orbit using Tsiolkovsky's rocket equation, which states that a rocket's ability to go faster or change its speed is dependent on two key factors. The first is how fast exhaust leaves the rocket, which measures the efficiency of the engine. The second factor is the ratio of the rocket's total mass at launch with fuel inside over the rocket's total mass without fuel. For example, a rocket with a higher mass ratio will go faster speeds, but most of its mass is fuel instead of other things like the capsule. To think of it more simply, the change in velocity, or delta V, is basically a budget using speed as its currency. As the rocket fires up its engine, it spends some of that budget. The full equation reads, the change in velocity is equal to the effective exhaust velocity, which is the speed of the exhaust, multiplied by the natural logarithm of the ratio of the mass with fuel over the mass without fuel. If we graph this equation, we can see that it gives us a logarithmic curve, meaning that as the mass ratio increases, the change in velocity increases as well, but with diminishing returns. This relationship forms the foundation of how all rockets fly, not just the Saturn V. With this equation, the workers behind the Apollo missions were able to find the change in velocity needed to reach Earth's orbit. The change in velocity was 9.4 kilometers per second to get into orbit from its launch site. But in space, the numbers were quite different. For the translunar injection, a propulsive maneuver that helped the rocket reach the moon, the change in velocity was around 3.2 kilometers per second. The rest of the change in velocity is used for the trip back. In total, the change in velocity, or delta V, required for the entire mission is 18 kilometers per second. And just for a side note, the change in velocity will now be called delta V. And back to the video. These numbers can help us calculate how much it would take to get to Mars. The first thing we have to do is get rid of all of the non-essential weight. Unfortunately, this means we can't bring anyone on board. This hypothetical mission will require around 14 to 15 kilometers per second of delta V to get to Mars. If we shave off weight by removing the life support systems, avionics, and other miscellaneous parts, we can reduce the weight by over 22,000 kilograms. That is 222,000 kilograms of the original weight compared to 200,000 kilograms of the new weight. This means we can add more fuel and increase the change in velocity to sustain the long burns we have to do when traveling to Mars. If we plug in the numbers for the rocket, we can achieve a total of 14 kilometers per second of delta V if we have proper staging. This means we can achieve a one-way trip to Mars. Now that we've done the math for this hypothetical situation, what would a simulated trip look like? Well, the first thing that would happen is the preparation of the Saturn V for this mission. This would mean stripping down all the parts of the original rocket to get the 200,000 kilograms of weight that we have to have. The second step would just be preparation for the launch, which would mean filling up the rocket with fuel and liquid oxygen. Next, the rocket has to be sent to Launch Pad 39A, which was designed for the rocket. Then, the launch procedures would go like normal. The mission control would call the launch, and the engines would be lit, launching the rocket into low Earth orbit. Around 68 kilometers up, Stage 1 will be jettisoned. And in low Earth orbit, We would have to jettison Stage 2. This stage will only be used for the flight up to LEO. Going up to LEO would take away around 9.4 kilometers per second of delta V, giving us around 4.6 kilometers per second of delta V to use for the trip to Mars. For the transfer to Mars, the Saturn V would have to perform a trans-Martian injection, which is similar to the translunar injection, where the spacecraft would have to light its engines to allow it to place itself in a Hohmann transfer orbit. You can think of this as throwing a ball from one moving car to another car. The cars have to be separated, like the distance between Earth and Mars, and not right next to each other so that the ball can reach the other car. Another way you can think of this is a highway merger. In a highway, you have to speed up to catch up to the speeds of the highway compared to the merging road. Nonetheless, the entire maneuver will take up around 3.6 kilometers per second of delta V from our total. This leaves us with a remaining 1 kilometer per second of delta V for the rest of the mission, including landing. To land on the surface of Mars, we have to use a specialized Martian lander to withstand the gravity and atmospheric temperatures of Mars. This may increase weight in the creation of this modified rocket, but for this experiment, we can just say that it didn't make a difference. Overall, the landing from low Martian orbit will take around 0.6 kilometers per second of delta V if we design a heat shield that covers the whole spacecraft that will deploy a parachute to land, giving us basically no delta V left. When we land on the surface of Mars, the only thing that could realistically happen is the deployment of Martian helicopters and rovers if we have space left from the modification. There is not enough fuel left to perform a departure from Mars. In summary, we can't get the spacecraft back if we try this mission. But it does answer our question, and that answer is yes, we can send the Saturn V to Mars. If you've reached this far into the video, I'd like to thank you for listening the entire way. With your support, this channel can deliver much more theoretical and educational videos like this one. Thanks for listening.